All right, so now we're going to take a look at some of the variables that we're going to see down the road when we start looking at electrical energy and electricity in general. We're going to introduce four right now, and then we'll see some others eventually. So the four most common variables that we're going to see in electrical energy are current, which is abbreviated I, uppercase I. We have voltage, which is abbreviated uppercase V, resistance, abbreviated uppercase R, and then we have power that we're going to throw in here that is abbreviated uppercase P. So we'll take a look at each of these in turn. I'll try to make some analogies to what these actually are going to represent. So current we can think of as the flow of electric charge through a conductor. And that conductor could be something like a wire, for instance. Okay, and then current is usually measured in amperes, which is abbreviated as amps, or just simply A, right? So you can think of an analogy to current as the following. So if you think of if you can imagine water in a pipe, water flowing through a pipe. All right, so there's the pipe involved, and then there's the end of it. So I have my water coming through here, and then it's flowing through to the other end. So when we talk about current being the flow of electric charge through a conductor, and this is usually represented per unit time. Okay, so in our analogy here, if I have my water coming through, well, the current would be analogous to that flow of water going through that pipe. So the faster the flow of water, in other words, the greater the current. Okay, so now we can think of, this is I'm trying to color code this. This is the water here going through, and then this is the pipe. Okay, the analogy, the water there would be that would be the electrons then, and then the pipe here would be the wire, for example. All right, so you have electrons going through this way through the pipe and coming out the other end. Okay, the greater or the faster the flow of those electrons, the greater the current is going to be. The greater the flow of water, obviously, the more water is going through the pipe per unit time, right? That's the analogy that we can think of. So the water flow there represents the electric current, and the pipe there represents the conductor, like a wire. Couple things that can affect the current. Okay, so faster the flow of the water, the greater the current. So this means then more electrons moving per unit time. Okay, would mean greater current. Faster moving electrons, I would say, would be an analogy here. The other thing that can affect the current is the size of the pipe itself. Okay, so obviously if you have a bigger pipe and the pipe is completely filled with water, more water can go through. Right, so a larger conductor, for example, can allow more electrons to go through compared to a smaller one. So this would allow more electrons to flow past per unit time. Hence, the greater the current. Okay, so when we talk about flow of electric charge, which is again due to the electrons through a conductor per unit time, we can define what's known as the ampere. So 1 amp, for example, is defined as 1 coulomb of charge passing through a point, some sort of a measuring point per second, right? That is what an ampere means. 1 coulomb per second. Okay, so 10 amps, for example, would be 10 coulombs per second, right? 100 amps, 100 coulombs per second. So that gives us an idea of how much of that charge is passing per second. Obviously, the higher the amperage, the greater the current, right? Another analogy that some people use is, maybe a stream, right? So you have a trickling stream, the water there representing the electrons. So a trickle in a stream, very low current, right? Very, very few electrons passing through, versus like a raging river, right? A lot more water, a lot more electrons going through, much higher current. All right, so that's the analogy there for current. The second thing we'll take a look at here is voltage. And when we talk about voltage in an electrical circuit or electricity generally, this is defined as the potential difference, chemical or electrical potential difference between 2 points in an electric circuit. And the key thing here is that potential difference between 2 points actually driving the flow of current. Okay, and then here we're thinking that as the electrons. Now, this is really important because why would electrons want to flow in the first place, right? Why would they want to move from one location to another location? Well, it's the voltage, which is a potential difference between 2 points, right? That difference causes electrons to move in a particular direction. So the symbol for voltage is V, and the unit here would just be the volts. And the volt is defined as 1 joule of energy per per coulomb of charge, right? So we have a volt being equal to a joule per coulomb. And we know that previously we saw an amp was a coulomb per second. So if we wanted to, we can substitute some of these in here. So from the above relationship, right? So we had an amp. So 1 amp is equal to 1 coulomb per second. We can rearrange this equation. We can say a coulomb, 1 coulomb is equal to 1 amp times a second. So if I take this, what a coulomb is equal to, and stick it in here, all I'm doing is just a little bit of mental gymnastics. I end up with a volt being equal to joule per amp second, right? So that's just another way by which we can kind of tie in some of these units to each other. But typically, this first relationship here is the one that we'll see. A volt is a joule of energy. Remember, a joule is a unit of energy per coulomb of charge. Just write that to the side here. So J here is joules. All right, so the analogy here, again, just to kind of, allow this to make a little bit more sense. So water pressure here would be the analogy. Right, so the pressure in the pipe is actually what causes the water to move from one direction to another, right? So higher pressure pushes more water through the pipe. So higher pressure So similarly, a higher voltage will then push more electrons through the wire or the conductor or whatever it is. So if the pressure drops, then less water will flow. If the voltage drops, less current would flow as well. Right. So again, maybe that makes sense. Maybe it doesn't make as much sense. But that's the analogy that typically that people use here to sort of make sense of some of these variables. So we talked about current, talked about voltage. The third thing we'll take a look at here is resistance. And resistance, abbreviated R, can be defined as the opposition to flow or to the flow of current in a circuit. Right? So as the name kind of tells you, it resists the flow of current in a circuit, abbreviated R. The unit that we're going to use for resistance is called an ohm, OHM, and it has the symbol, it looks like this. That's the symbol omega, and that's what we use for ohms. And we define an ohm, so 1 ohm, or this is equal to 1 volt per ampere. Okay, so we saw voltage before as being equal to joules per coulomb. Now we're saying an ohm is equal to 1 volt per amp. So resistance will depend on several things. Okay, it'll depend on the material. Okay, what type of metal wire is it, for example? The length of the wire or the conducting material, cross-sectional area, among other things. These will all affect the resistance of a particular substance. So current, the flow of electric charge through a conductor per unit time. We have voltage, which is the potential difference between 2 points in an electric circuit that drives the flow of current. And you have resistance, which is the opposition to the flow of current in a circuit. These are all related to each other. Those three things are all related to each other by what's known as Ohm's law. Okay, so Ohm's law relates voltage, current, and resistance in a very simple, very simple equation. So V is defined as being equal to the product of the current I times the resistance R. Okay, and then being a mathematical equation, we can rearrange this to solve for any of those other two variables. Okay, so for example, I current would be equal to V voltage over R by rearranging this. Similarly, we can say the resistance would be equal to V divided by the current I. Okay, so these are all just alternative ways to express the relationships between those three things: voltage, current, and resistance. V equals IR is probably the most common one that you will see. All right, so let's put these all three together now in just a very simple circuit that's shown here. So we have on the left side, the thing that I'll highlight in pink, that's your, let's say we have a battery. And as you know, we have two of these in connection to each other. We have a positive end to the battery and we have a negative end to the battery, right? And that battery, let's say it's a 9-volt battery. Okay, so now we know volts, right? That is that's the voltage that is giving us an indication of the potential difference between one end of the battery, the positive end, and the negative end. And if we connect those two ends with a conducting material, so like this thing here would be our wire that we're using, okay, as our conducting material, this potential difference now will force electrons to move in a particular direction. And electrons move according to the electrostatic force. They will move from the negative terminal, right? Because they're going to be repelled from the negative terminal, and they're going to move towards the positive terminal along this wire. So they move in this general direction. That is how the electrons flow, right? So your electrons flow from the negative terminal of the battery to the positive terminal. Okay, they go towards the oppositely charged thing. Now, the flow of current is actually defined in the opposite direction. So when we talk about the current, current is defined as going from the positive end to the negative end of the battery. Okay, so that's something to keep in mind when we talk about and again, this stems historically from how people thought about electrical current back in the day. But it's important to start with how are the electrons going to move? Well, we know electrons are negative. They want to go towards something oppositely charged, which is the positive terminal, right? So that's how they're going to flow. Conventional current is going to flow in the opposite direction. So what we can also do here is we can, put in this circuit something that has some sort of a resistance, and in this case, it's a bulb. And then if current flows through it, it will cause the bulb to light, and then this will provide some sort of a resistance in whatever that happens to be. All right, so that's something to keep in mind when we look at circuits generally, and we're not going to get too deep into this. This is just to give you an idea of how those are connected. So the voltage, the potential difference here in the battery, that's what forces electrons to move in the first place. They're going to move from the negative terminal to the positive terminal. Conventional current goes in the other direction, in this case, causing the bulb to light. So we can take a look at a very simple example of this. So let's say a circuit for example, has a 12-volt battery in it and a resistor of 4 ohms. Okay, what's the current flowing through this circuit? Okay, so again here, when you're given these types of problems, kind of list what you have. So we have voltage being equal to 12 volts. We have the resistance being equal to 4 ohms. And then what we need to find is the current, right? So we need a relationship that connects these three. Well, we know, we just talked about V equals I times R. I need to solve this for I. Okay, so I'm going to divide the right side by R to get rid of it. That means I need to divide the left side by R as well. All right, so I end up with the current I being equal to V over R, and I'm just going to substitute those into my equation. V is 12 volts. We have R, the resistance is 4 ohms. 12 divided by 4 would give us 3 amps as the current flowing through the circuit. All right, so fairly straightforward thing, but you want to make sure that you know how to rearrange the V equals I on our equation.